So that's light as a wave, and the reason, well, that was sound as a wave, but light as a wave is the same idea. And it was really established by the early 1900s that, in fact, light behaved as a wave. And the reason that it was so certain that light was a wave was because we could observe these things. We could see, for example, that light diffracted, and we could see that light constructively or destructively could interfere with other light waves. And this was all, confirmed and visualized. But also around the time that Thomson was discovering the electron, there were some other observations that were going on. And the most disturbing to kind of the understanding of the universe was the fact that there were some observations about light that didn't make sense with this idea that light is a particle. And the photoelectric effect is maybe the most clear example of this. So the photoelectric effect is the effect that if you have some metal, and you can pick essentially any metal you want, and you shine light of a certain frequency onto that metal, you can actually pop off an electron, and you can go ahead and measure what the kinetic energy of that electron that comes off is, because we can measure the velocity, and we know that kinetic energy equals 1/2 mv squared. And thanks to Thomson, we also know the mass of an electron. So this is an interesting observation, and in itself not too disturbing yet, but the important thing to point out is that there's this threshold frequency that is of the metal, and each metal has a different threshold frequency, such as if you shine light on the metal where the frequency of the light is less than the threshold frequency, nothing will happen. No electron will pop off of that metal. However, if you shine a light with a frequency that's greater than the threshold frequency, you will be able to pop off an electron. So people were making this observation, but this wasn't making any sense at all, because there was nothing in classical physics that described any sort of relationship between the frequency of light and the energy, much less the energy of an electron that would get popped off of a metal that would basically come off only when we're hitting this threshold frequency. So what they could do was actually graph what was happening here, so we can also graph what was happening. And what they found was that if we were at any point below the threshold frequency, and we were counting the numbers of electrons that were popping off of our metal, we weren't seeing anything at all. But if you go up to the threshold frequency, suddenly you see that there's some number of electrons that comes off, and amazingly, the number of electrons actually had no relationship at all to the frequency of the light. And this didn't make a lot of sense to people at the time, because they thought that the frequency should be related to the number of electrons that are coming off, because you have more frequency coming in, you'd expect more electrons that are coming off. This wasn't what people were seeing. So what they decided to do was just study absolutely everything they could about the photoelectric effect, and hope at some point someone would piece something together that could explain what's going on or shed some light on this effect.